From this point on, we are gonna try to create higher and higher quality images. We already solved the problem. We can generate images. Perhaps we can generate low resolution images. They are gonna look good, but they are not yet production ready. We cannot sell it to a customer and make your customers happy because they are setting high bars. If there are any minor glitches in the generated images, they're not going to be happy. So from this point on, we want to make things perfect or as perfect as possible. The video for this slide is online, so you can watch it. But what is the big picture? And then you can ask questions. The idea is generating and discriminating between low resolution images is easier for multiple reasons. First of all, these are low dimensional distributions. The other reason is you have less parameters to train. There is less chance for overfitting, and therefore you can train those architectures faster. And the idea is to progressively grow the resolution. The idea is beautiful. You take it behind the computer, you try to code it, and then things are not going to converge. The reason is if you are at 4x4 resolution, and then let's say you have a convolution that's doing that for you, then suddenly introducing new parameters to your architecture is going to introduce discontinuity. So your system is going to go through a shock, and it's going to forget whatever that it learned for low resolution stuff, and then it's as if you didn't have that step before it. So you have to gradually introduce these 8x8, 16x16, 32x32 resolutions slowly. And that's the idea here. You start with something that is operating, or an architecture that is operating at 16x16 resolution. If alpha is 0, all you're doing now while making the transition to 32x32 resolution is just introducing upsampling and downsampling through this route. So if alpha is 0, you're going to go through this route. But then you gradually increase alpha. You give it a schedule, like a learning rate schedule. You're going to have a schedule for alpha. And after a couple of iterations, you're going to set alpha to be 1, and you're forgetting the other route. And then you gradually introduce this 32x32 layer. That's the idea, the big picture. There are some minor details here. One of them has to do with the fact that you should avoid mode collapse. And we saw a technique for doing it before when we were talking about improving the training of GANs. And the idea was, don't look at a single example at a time, look at multiple examples. And this is another way of looking at multiple examples. The way that you're going to do it is you're going to take n examples at some particular feature map, and then you're going to turn this 512 into 513, and that additional channel is going to correspond to the average of the other guys. So you're doing some averaging over n, and your pixels and your channels. And all you're doing is broadcasting a scalar and concatenating it on top of 512 as an additional channel. And this way, you are not looking at your examples individually. Your examples have a baseline to compare with. And the baseline is always the last channel. And perhaps this is going to help your model escape the mode collapse. And there are also some other details, like you want to have equalized learning rates while training your parameters. And the way that you're going to do it is, rather than optimizing over W hat, you're going to optimize over W's, which are all initialized the same way, with mean 0 and standard deviation identity, regardless of what is your filter size, what is your number of input channels, output channels. They are all initialized uniform in a uniform fashion using the normal distribution. So this is just a change of coordinates, and your optimizer is going to see W. It's not going to see W hat. And then everything is going to have an equalized learning rate. The other thing that is really important is this local response normalization. Now you're starting to see that we are going beyond batch normalization, layer normalization, group normalization. We are introducing new normalization techniques just for GANs. And this is one of them, local response normalization, and then you can have different loss functions. So this paper was about the architecture. and the training process. And from this point on, usually a good technique that you're going to know about and perhaps use it in your research is going to be progressive growing idea. Any questions about progressive growing? Was everything clear? Okay, perfect.